let us talk about tangent, secant line, and then we're going to extend the idea to the definition of limit. So our objective is tangent line. I'm going to start this by giving you one example. Suppose we have a function y equals to x squared. Well, I'm interested in finding an equation of tangent line to the graph of this function at a given point. Find equation of tangent line to the graph at point x equals to, let's say, 1. What is equation of tangent line? Let's write down this recall here that to find equation of any line, we need one point and the slope of the line. We need one point, like x sub 0, y sub 0, and the slope of the line, which is m. So remember that it's y minus y sub 0 equals m times x minus x sub 0. So here you have a function, y equals to x squared. Here you have x, here you have your y, and this is the graph of your function. 1 and 1, 2 and 4. So let us connect this together. Top. Suppose this is the graph of your function that you have. Because of symmetry, it's going to be the same on both sides. So our goal is to find equation of a line which is tangent to this graph at 1. So 1 is here, 1 and 1. We're interested in finding equation of this line. What is the equation of this line? What is y equals to mx plus b? How do we figure this out? How do you suggest the approach finding the equation of this tangent line? Well, what they did suggested before was, okay, we're going to take 2 points. Instead of working with just 1 point, like 1, we're going to take a nearby point and find equation of the secant line instead of tangent line. We can take a nearby point, x equals to 1.1, or you might say, why not take 0.9, close to 1 from left-hand side or close to 1 from right-hand side. X equals to 1.1, and find the equation of the secant line passing through two points, 1 and 1, and 1.1 and 1.1 squared. So I have my first point, I have my second point, I can easily find the slope. I have one of these points, write down the equation of the line is easy. It's not exactly the same as the tangent line, but it's good enough. So m is equal to 1.1 to the second minus 1, difference in y values, over difference in x values. Very well. So 1.1 raised to the second power. Let us calculate that. (1.21) minus 1 divided by, here you have 0.1. So we get 0.21 divided by 0.1. We get 2.1. This is the slope of the secant line. Now, the equation is y minus y sub 0 equals to m times x minus x sub 0. So y is equal to 2.1 x minus 2.1 plus 1 minus 1.1. This is not the tangent line. This is not exactly this line, but this is close enough. We are taking this point here, 1.1, and this point is on this part of the graph, so it's going to be a little bit tilted. This is your secant line, not the tangent line. But they are close enough. You might take another point on the left-hand side, 0.9, and start calculating the whole thing one more time. So we found equation of secant line. Which is not the same as tangent. Okay, so what should we do now? The question says, hey, find equation of tangent line, not the secant line. Well, what I'm going to do, I'm going to increase the precision here. I'm going to make this guy very close to 1. I'm going to add more decimals on the right-hand side. Well, how close I can get? If I add, for example, 3 decimal places, if I add 4 decimal places, a number which is close to 1, or I might use a number before 1. How close it can get? 0.99, 0.999, 0.9999. Which one? Which one gives me the best answer? So as we get closer and closer, and we get numbers that are closer and closer to 1, you're defining something that is the limit. You're getting closer and closer to 1 from right and left, and this secant line eventually going to be the same as tangent line. But we have to increase the precision for these numbers. That's where limit come from. Limit of a function is actually finding the y value of the function as we get closer and closer to x on horizontal line, and on y-axis we get closer and closer to y as x approaches the number on x-axis. Very well. So in this example, we have a ball suppose a ball is dropped out of a roof of a building which is 450 meters above the ground. Question says, well, find the velocity of the ball after 5 seconds. Velocity of the ball after 5 seconds. Okay, very well. So what are we going to do? We're going to use the formula for the distance, ST, that you learned in physics, 4.9 times t squared, the distance formula. Very well. Okay. Can I find the instantaneous velocity? Is it possible? Or I can only find the average velocity? In this case, I'm only able to find the average velocity. You can only find the average velocity, which is not the same as instantaneous velocity. It's almost, you can say that, maybe close. To find the instantaneous velocity, we need to use the definition of limit. Okay, very well. What are we going to do? We're going to use y values, the difference between y values over the difference between x values. So let us select a number close to 5. Close to 5. You can say, hey, I'm going to use 4.9, or you might say, I'm going to use 5.1. So my x sub 0 is equal to, let us write down t sub 0. T sub 0 is equal to 5, and t sub 1 is 5.1. Close to 5. You can increase the precision by writing this number with more decimal places to make it closer and closer to 5. Okay, now what do we need? We need the y values. What is the first y value? Here, you need to find s of 5, and also you need to find s of 5.1. These are your y values. These are our y values. Okay, 4.9 times 5 squared, and here you have s of 5.1, which is 4.9 times 5.1 squared. So the average velocity, not the instantaneous velocity. It's like tangent line and secant line. The average velocity is equal to s of 5.1 minus s of 5 divided by 5.1 minus 5. Just again, we're substituting these here. .9 times 5.1 squared minus 4.9 times 5 squared divided by 5.1 minus 5, which is approximately is going to be 49.49 meter per second. Again, here we are asking this question. Is this going to be exact velocity at 5 seconds? No, it's not the exact velocity. We only found the average velocity. So these types of questions gave rise to the topic of limit, how we can find the exact value. We're going to use the definition of limit to actually calculate the instantaneous velocity, the equation of tangent line, easily finding those values. So as you can see, we need a new tool, we need a new technique to help us find the instantaneous velocity, the instantaneous rate of change, the instantaneous speed, or you need to find the slope of tangent line. We cannot just rely on the average velocity or the slope of secant line to find those. We need to introduce something new that we call the limit of a function. Okay. Let's define the limit, then show you how to use the limit to find and solve these problems. The limit of a function. So definition, suppose you have a function. Let y equals to f of x be a function. The limit of the function at point A is represented this way. The limit of the function at x equals to a number like a is denoted by we write lim representing the limit of f of x. We're writing down either y or f of x. It doesn't matter. It's not important as x approaches a. So we read it as limit of f of x as x approaches a. So take a look at this graph. X-axis, y-axis. Suppose we have a graph of the function like this. This is your y equals to f of x. This is your function, and you have a on x-axis. The limit of the function is going to be a value on y-axis. So we're getting closer and closer to a on x-axis, and our y value is going to be our limit. So this number, whatever it is, let us call it L. It is equal to the limit of the function. Limit of f of x as x approaches a. So limit of a function is y value. Note that the limit is a y value. It's not an x value. We are getting closer and closer to A on the horizontal axis, and our y approaches L. L is going to be the limit of function. Let's write down some examples to feel more comfortable about finding the limit. As I mentioned, some functions are well-behaved. In the next session, we're going to classify well-behaved functions and not so much well-behaved functions. So some examples, give us an example. What's going on here? I'm going to give you nice function and then not so much nice functions. Suppose you have this function. I'm going to give you y equals to x squared, and I'm going to ask you to find the limit of y as x approaches to 1. Okay. Another example for you. B. I'm going to give you this function. Y equals to x cubed, and I ask you to find, hey, what is the limit of x cubed as x approaches to 2? C. I'm going to give you this function. This is a piecewise defined function this way. Okay, here we go. X-axis, y-axis. Let's take a look at the behavior of the function. 1, 2. And here you have 1, 2, 3. So this point is not on the graph of the function. And then you have another point which is not on the graph. 3, 4, 5. And here you have another hole in the graph. Okay, and we have a point here. So this is your crazy looking function. And for this function, find the limit of, let's call it function g of x, as x approaches to 2 from left. Find the limit of g of x as x approaches to 2 from right. And finally, what is the limit of this function as x approaches to 2 itself? So how did we define the limit of the function? Our function y is equal to x squared. Okay, it means that we are finding the limit of x squared as x approaches 1. As x approaches 1, here you have 1 on x-axis. What is the y value of the function? Well, when x is 1, my y is 1 as well. So this is your limit. As x get closer to 1, the y value is 1. 1 squared is equal to 1. This is our limit. Limit of y as x approaches to 1. Very well. So for this function, x to the third, as x approaches to 2. Well, okay, as x on horizontal axis approaches to 2, well, what is my y value? This is my x. My y value is going to be 2 to the third or 8. This is my limit. 2 to the third, 2 times 2 times 2, which is 8. Guys, 2 to the third is not 6. 2 to the third is not 6. Well, what about function g of x as your x approaches to 2 from left-hand side? We are getting closer and closer to x, 2 from left-hand side. What is my y value? So what does it tell us? It says, hey, I'm going to get closer and closer to 2 from left-hand side, So I'm getting closer and closer to 2 from left-hand side. It means that I'm working on this part of the graph. What is my y value as I'm getting closer and closer to 2 from left-hand side on this part of the graph? It is equal to 3. This time, I'm getting closer and closer to 2 from right-hand side. From right-hand side, let me use a different color. I'm getting closer and closer to 2 from right-hand side. From right-hand side, I have to ignore left-hand side graph. I'm not working with this part. I'm just working with this part of the graph. As your x getting closer and closer to 2 from right, you are working with right-hand side of the graph. What is the y value getting closer to? It's getting closer to 1. Here we go. This is your limit. So, do we have a limit at 2? If we have a limit at 2, it's either 1 or 3. Okay, which one is that? Common sense. Since 1 and 3 are not the same, the limit at 2 doesn't exist. We don't know which y value to associate it with g at 2. So you write down, does not exist since 1 is different from 3. You have 2 different y values. Which one is the y value of the function at 2? It doesn't exist.